And very good evening. Today we will be discussing about the regiochemistry of during the electrophilic substitution reactions. This is slide number 58. I think you are all here. Just look at the slide number 58 on the PowerPoint that I have already provided. So you can check the slide number 58 on those. So far we have studied that when we are dealing with the benzene ring, when we are doing this electrophilic substitution reaction of benzene without having any substituent, then there is no problem, because any hydrogen of the benzene can be replaced with the electrophile, the coming electrophile. But what about the situation where there is a substituent already attached to the benzene ring? Under that conditions, if there is only one substituent, that substituent, the nature of that substituent usually depends whether that substituent is electron donating or the electron withdrawing. So that substituent has to decide that which of the proton will be replaced with that coming electrophile. And sometime also we have discussed yesterday that there is a possibility of more than one substitution of the electrophile. Under that conditions, we will have the substitution at more than one position. So the bottom line is that there is a all these things depends upon the nature of the substituent that is attached to the benzene ring. We already know that some of the substituent which are very high electron withdrawing group, what could be the direction of the coming electrophile? You, I think, already know about the directive influence of the existing substituent on the benzene ring. So it's all depends upon. You can see this in this picture that I have provided you. This is slide number 58 of the PowerPoint presentation that I have provided. Here you can see that if there is a strong electron withdrawing group, that is like the any carbonyl groups, or there is a strong like the fluorine or the other electron withdrawing group, then definitely there will be the coming electrophile has to come on the meta positions. But if there is an electron donating group attached to the benzene ring, then you already know that the preferable positions for that will be the ortho and para. So all the electron rich species, they are the ortho para director, while the electron withdrawing groups, they are the. So the question is that why this happens. Actually, when the electron withdrawing group is attached to the benzene ring, it usually decreases the electron density at the ortho and meta positions. So the ortho and meta positions, they are electron deficient in the event when we have an electron withdrawing group attached to the benzene ring. Under that conditions, the only electron rich center would be the meta position. That's why this meta positions, which is electron rich, attack on the electrophile, coming electrophile, and then what happens, the electrophile is then attached to that meta positions. But if we are introducing the electron donating group, you already know that by drawing all the resonating form of that structure, we will come to know that the electron density is usually more on the ortho and para positions. compared to the meta positions. That's why the possibility of the coming electrophile will be the ortho and para positions. That's why they are the electron donating groups. They are ortho. Sometimes and para. We also call those the electron donating group. They are called the activator group because they activate the ring, pushing the electron density more at the ortho and para positions, and we can say that the overall density of the electron is increased on the benzene ring. That's why they react on the ortho and para positions, and that's why they are called the activator. But on the other side, the electron withdrawing group, which instead making the benzene ring even more electrophilic rather than nucleophilic. That's why they are called the deactivator. Activator group will be faster for the towards electrophilic substitution reactions compared to the deactivator, which decrease the rate of the reactions because actually the reaction is very slow. You can see that on the slide number 62 and 63. I mean, the trend of reactivity this can be evident from this. That is the nitrobenzene, chlorobenzene. They are the first two, in fact. The nitrobenzene, the chlorobenzene, they are the deactivator. That's why their rate of the reaction towards nitration would be less than benzene. On the other side, the activator group, that is the OH group attached to the benzene ring, that is called phenol. The rate of the reaction is in fact 1000 times faster than that of benzene. Because this OH group is an electron activator, it donates the electron density towards benzene. That's why the rate of the nitration, which is the electrophilic substitution reaction, would be higher than that of benzene. Slide number 65. If we compare the, let's suppose we compare the rate of nitration of benzene ring with any of these, like the nitrobenzene, chlorobenzene, and benzene, and then that of the phenol, you can see that the compared to the benzene ring, right, compared to the rate of nitration of the benzene ring, the nitrobenzene is 6 into 10 raised to power minus 8 times slower, the rate of the reaction. What about the chlorobenzene? So if benzene is 1 time, it means that the chlorobenzene will be 0.033%. Still, why is this? Just because the chlorine has the electron donating capability, but still it is an electron electronegative atom. It does have the electron withdrawing capability also, because being negative, it can push the electron towards itself. What about the phenol? You can see that OH group is now, this is a strong electron donating group, and that's why the reaction of phenol will be 1000 times faster than the the nitration reaction of the phenol will be 1000 times faster than the nitration reaction of the benzene. So you can see here in this diagram of the showing the reactivity trends in reactivity. You can see that the groups on the central one is representing benzene ring, and on the left side of the of this arrow you can see that electron withdrawing group has been given. Those electron, almost all those all the groups, electron withdrawing group, they are the meta directing and they are deactivator, because they are decreasing the electron density inside benzene ring. On the other side, on the right side, you can see that all the groups, they are electron rich. That's why they are donating the electron density towards benzene. They are the ortho and para director that we already know, and they are the activator group because they are increasing the electron density on the benzene ring. But what about the central groups like the bromine, fluorine, iodine, chlorine? At one side we see that they have the electron withdrawing capability, being highly electronegative. On the other side we see that they are also electron rich. So we can say that being electron rich, they are the orthopara director, no doubt, except fluorine. They are the orthopara director, but on the other side we see that they are also decreasing the electron density on benzene ring by minus I effect. So it means that you already know about the inductive effect and the mesomeric effect. Mesomeric effect, you see this through space, and the inductive is through bond. So they are pushing the electron density from the benzene ring. That's why they are the deactive. But on the other side, since they are rich in the electron, that's why they are called the you already know activator about the group. Inductive and mesomeric effect. Inductive effect, you know that it withdraw or donate the electron through sigma bond. If the electron donation are withdrawing through the sigma bond, then we say that this is inductive effect. It's evident from the name induction, right? On the other side, you can see the mesomeric or the resonance effect, where electron donation or electron withdrawing is through pi bond. If the pi bond is involved in the electron withdrawing or with electron donating, then we say that this kind of the effect is called the resonance effect due to the overlapping of the p orbital on the substituent with the p orbital of the aromatic ring. So that's why they are called as the this is called the mesomeric. For the halogens, the reaction would be the orthopara directing. But on the other side, since they are not increasing they are decreasing the electron density in benzene ring, so the reactions of the chloro, bromo, iodo, and fluorobenzene would be very slow. They will be very slow because they are orthopara directed, but they are deactivated. Slide number 68, where you can see the nitro group, the cyanide group, C triple bond N group, are the acetyl group. They are all electron withdrawing group. They are pushing the electron density from the benzene ring. And on the other side, you can see that with the halogens, they are also up to some extent the electron withdrawing, but the electron density is under that case only withdrawn from the meta positions, and then the only position left is the ortho and para positions rich in electrons. That's why that they are feasible sites for the feasible sites. They are which abstract the coming electrophile. Draw the various type of, this is a small kind of the homework. You can do that. It's not a homework, but you can do that. You can practice on it, just like draw the various substituent, and then write the plus m minus m plus I minus I effect, right? Mesomeric plus m effect minus m effect plus I effect minus I effect, and then categorize those all the derivatives of benzene based on that. You will understand that what could be the which one will be the feasible, which one will give the highest rate of the reaction towards nitration, sulfonation, or any other kind of electrophilic substitution by keeping in view one other factor that we are for the time being not thinking about. Just think about the, during the electrophilic attack, we have a carbocation formation at the benzene ring. So just think for a while that whatever the substituent on the benzene ring stabilize the carbocation will be the one that will have a faster rate of the reaction. In case of the electron withdrawing group attached to the benzene ring, you can see that this a carbocation which is generating after the electrophilic attack is electron deficient center, and if benzene have the electron withdrawing group attached to it, it will further destabilize the system. We have so far studied that whatever stabilize the carbocation, that will be the favorable substituent. In case of electron donating group, if we have electron donating group, the carbocation which will be result after the electrophilic attack will be stabilized by the electron donating group. But this is not the case when we have the electron withdrawing group, because if we have the electron withdrawing group, after the electrophilic attack, carbocation will be formed, and then that carbocation will be destabilized by the electron withdrawing group, because that is already electron deficient, that carbocation. And we are further trying, that electron withdrawing group is further trying to push the electron from the carbocation, that will destabilize the system further. So that's why we call those as all those the electron withdrawing group, they are the deactivator, and the ones having the electron donating group, they are the activator. So for the deactivator, the reaction will be very slow, and for the activator, you want to see that which of those is more stable. The very simple thing is that just draw the number of resonating form. For that, anyone that anyone that outrange the number of the resonating form, that in fact you can say that anyone that has the greater number of the resonating structure could be the most stable one. So here is one of practice for you. I'm not showing you the title. Without seeing the title, just be honest. Let's try on it. Can you please tell me that what all of these pictures predict? What they predict? What kind of the sense we can develop after seeing these pictures? Can you please tell me? Reply me if you. However, one thing is very important to note, that if any group, that is the ortho-para directive, it doesn't mean that it will not give the meta product. It can give the meta product as well, but that meta product will be very less in quantity. For instance, if we are talking about the nitration reaction of the toluene group, the 63% of the product would be the one where the attack will be on the ortho positions. So 63% of the product will be the ortho nitrotoluene, and 34% will be the product that will be the para nitrotoluene, and just 3% of the product will be the meta nitrotoluene. So you can say that we cannot exclude that possibility of the meta product in case if we are dealing with the ortho para directing group. There's a possibility in fact there is a formation of the nitro product as well, but that will be very much less in quantity compared to the ortho and para. So the trend is that the more ortho product, some medium in quantity, the para product, and the very less product would be that. But I didn't get your proper answer. But let me tell you that you can see that in the first picture, where this on the left side, extreme left, the picture of the where a nitrile group, CN group, is attached to the benzene ring. It's called the benzonitrile. You can see that the electron density, which is reddish in color, just first of all, just look at the benzene ring. You can see that the central of the benzene ring is reddish in color, It means that this reddish color represents the electron density. But as we are moving away from the benzene towards left, we see there is a little bit electron density that has been withdrawn above, right, towards the substituent. The substituent is chlorobenzene. So substituent is chlorine group. The chlorine atom is withdrawing a little bit of the electron density out of the benzene ring. So you can say that there's a very light reddish color, and some of the reddish color transfer to the top. On the other side, on the benzonitrile, you can see that all the electron density has been withdrawn, and this has been shifted towards the CN group, right? Just look at the right side of the benzene ring. You can see the toluene group. Now this reddish color is deepened compared to benzene. It means that further electron density has been donated by the toluene group, methyl group. But if we look at the extreme right section, right part picture, we can see that the electron density is even deeper in the aniline group, because aniline is a strong electron donating group. So this represents this is also the order of reactivity towards electrophilic substitution reaction. That more richer the benzene, any group that make the benzene ring more richer in electron, that will be highly reactive towards electrophilic. So this was the end of this lectures. I welcome any of your question at this stage if you have any. Hopefully we will be continuing this by tomorrow. The question arises that if we have two substituent, one of the substituent is the ortho-para directing, and the other is the meta-directing group. So both of the substituents, they are present at the same time. So now question is that the coming electrophile will be directed or will be attached to which of the positions. So who will decide the orientation of the coming group? Now that is the question. So if this is the situations where the methyl group or the nitro group, they are present at para position to each other, under these conditions they will have the same additive effect. You can see that nitro is the meta directing, so it means that it has to be attached at the position that will be ortho to the methyl group, and that's what it is. The nitro group is coming at the ortho position. So by doing this, both of the problem will be solved, because the nitro group will be attached, after attaching the nitro group to the at the ortho positions to the methyl group, both of the problem will be solved. It is now ortho to the methyl group and as well as meta to the but what about when we have the OH group and the methyl group? They are para to each other. The one that I have shown you on the slides just now. You can see that the coming electrophile can go either way. It can come ortho to the OH group, or it can come ortho to the methyl group. So there are two available options. Now the question is that which way it has to go, whether it should be ortho to the methyl group or it should be ortho to the OH group. Who will decide? For this purpose, this has not the same effect. This has opposite effect. So if this opposite effect means that one of the group which is being more activating will decide the orientation of the coming electrophile. It means that if we compare the OH group and the methyl group, so OH group has more capability of the electron donations. So it is more activating because both the OH as well as the methyl group, they are electron donating, but under different concepts. OH group is mesomerically electron donating. Methyl group could also be mesomerically, but its effect is not that much strong because the every proton of the methyl group can be mesomerically electron donating as well as inductively electron donating. But the mesomeric effect of the OH group is predominant. The reason is that it has apparent electrons on the oxygen that can be donated to the ring very clearly compared to the methyl group, which doesn't have the lone pair or the non-bonding electrons that can be donated to the ring. That's why we say that the OH group that is more electron donating, and that's why it's more activating group. Every group that can donate electrons to the ring, apparently we say that that's more electron activating. And you already know that any group which withdrawn electron more actively, we call that's more deactivating. So here in this case, the OH group will decide the orientation of the coming electrophile. That's why bromine is attached also to the OH group. Slide that the OH group has the electron donating capability through the mesomeric effect or the resonance effect. Now question is that what is the difference between the mesomeric effect, which is also called the resonance effect, and the inductive effect? Someone has asked this question yesterday. So the answer for that is that mesomeric effect or the resonance effect, this is through space, which means that some of the apparent electrons, they are available, which are showing direct transfer of the electrons to the system, maybe to the ring. So there's a direct transfer of the electrons. That electron is to space. You can see that. So that's called the resonance or the mesomeric effect. Both of the names are used for the same thing. This can also be shown. This can be of two types. This may be plus M or minus M, which means that plus mesomeric effect and minus mesomeric effect. On the other side, there is called the inductive effect. Inductive effect is the effect in which the pulling or the pushing of electron is through sigma bond. So inductive effect is evident from the name induction. So it means that either it can donate the electrons towards the ring by the pushing the electrons or through induction through the sigma bond, or it can withdraw the electrons through the sigma bond. So how we can differentiate between the inductive effect and mesomeric effect? So inductive effect, just like the mesomeric effect, inductive effect can also be of two types, plus I, minus I. So there comes a total of four types of the effects. One is called the plus M effect, other is called the minus M. Similarly, one is called the plus I effect, the other is called the minus I effect. Just take that an example, it will be clear to you. If you look at the phenol, right? In phenol, you see that the OH group has apparently some electron pairs that can apparently go towards the benzene ring through space. Now this is not through the bond, but in fact it is moving. You can see that with the arrows, that it's moving directly towards the ring through space. That's why it's not through bond. That's why it's making a different type of the resonating structure. You can see that in this structure, in this figure that I have just shared. In this figure you can see that all the electrons, they are moving and they are resonating on the various ortho and para positions. So that's why this is called the mesomeric effect. This is plus M effect, right? On the other side, because this is moving through space, on the other side, just take an example of the nitro group. So nitro group, you can see in the nitro group, the electron pairs is pushed from the benzene ring. So apparently it's showing that the electron pair is moving from the benzene ring and it's making different type of the resonating effect. So it is showing the minus. So in the slide you can see that the nitro group is the electron is trying to withdraw the electrons from the benzene ring through space. That's why it's called the minus M effect. That is called the mesomeric effect, but it is minus M effect. On the other side, if you can see that what about the CF3 group, if that is present on the benzene ring? If CF3 group is present on the benzene ring, you know that the fluorine has the electronegative nature, so it will be withdrawing electron density from the benzene ring. That's why through the bond, through the sigma bond. So there will be an induction, so you can represent that by an arrow. That's why this is called the induction, because it is inducing the electron density. So it is pulling the electron density from the benzene ring through the sigma bond. That's why it is called as the is it plus M or is it plus I or minus I? So it's minus I because it's withdrawing the electron density from the benzene ring. But what about the plus I effect? Can you give an example that represents the plus I effect? So just look at the methyl group. You know, methyl group, as I have shown you, that methyl group has the capability where it can show the hyperconjugation. So hyperconjugation actually represents the resonance or mesomeric effect, right? Because that's the through the flow of electron towards the benzene ring. But you can, on the other side, the methyl group is also showing the plus I effect, inductive effect. How? Because the sigma electron, they can be pushed towards the benzene ring. The three of the hydrogen single bonds, sigma bonds, they can be pushed towards the rings. So that's why they are pushing the electron density through the sigma bond. That's why they are also, this represents the plus I effect. So methyl represents the methyl. If toluene, just take the example of toluene, where the methyl group is attached to the benzene ring. This by pushing the electron density through the sigma bond to the ring represents the plus I effect. But if the CF3 group is attached to the benzene ring, since fluorine is more electronegative, so it can push the electron, it can pull the electron density from the benzene ring through the sigma bond. That's why it's called the minus I effect. Methyl toluene is this example where which can represent both of the effect at the same time. It's representing the inductive effect as well as the mesomeric effect. Because if you take the example of the hyperconjugation, hyperconjugation is actually represents the example of mesomeric effect. Which mesomeric effect? It is the plus mesomeric effect. But on the other side, the it also represents the inductive effect, plus inductive effect. So plus mesomeric effect plus inductive effect. How? Because it is donating the electron density through the benzene ring. So you can see as a whole that we say that the methyl group is the ortho-para director. So it is ortho-para director under both the inductive as well as the mesomeric concept. Because if we take the mesomeric concept in the mesomeric effect, the hyperconjugation is the example. So the methyl group is ortho-para director under both the mesomeric and inductive effect, because in the mesomeric effect the hyperconjugation represents that the methyl group is the electron donating, and especially at the ortho and para position. On the other side, the inductive effect, it also shows the electron donating capability through the inductive effect by pushing the electron density of the hydrogen to the towards the benzene ring. Nitro group, if attached to the benzene ring, that represents which effect? You already know that it's also through the space, it pulls the electron density. That's why it's called mesomeric effect. If OH group is attached to the benzene ring, that represents that it is apparently contributing the electron, pushing the electron towards benzene ring. That's why it's representing the mesomeric plus mesomeric effect, OH group in phenol. Nitro minus mesomeric. What about plus I minus I? CF3 attached to the benzene ring represents minus I effect, but if methyl group attached to the benzene ring represents the plus I effect. So in this way you can continue, and I have also shown you one of the slide where you can compare the electron donating and withdrawing capability order of electron good activating group, that which one could be good electron withdrawing. So you can see that order in the slides, that which will be the powerful electron withdrawing. What about this example where the if the methyl group is attached matter to the chlorine group? Under that conditions, if we subject this compound towards the halogenation, especially to the chlorination under the Lewis acid, what the coming electrophile will be coming on? Whether it will be coming in between the methyl group and the Cl group, or it will be coming on the other two arrows, that the double arrows, two of the double arrows that has been shown on either side. So in the initial condition, if we bring the coming electrophile between the methyl group and the chlorine group, you can see that there will be a steric hindrance offered by this methyl group. That's why this is the least feasible position for the coming electrophile. But on the other side, you can say that we have to adjust the coming electrophile onto the benzene ring in such a way that we should not disturb the order of orientations, because you know that both the chlorine and the methyl group, they are both ortho-para director, right? So both of these, they are ortho-para directive. Now question is that the coming electrophile, it can't go between the two groups, that is the methyl and the chlorine. So the only two available positions for that has been shown by two double-headed arrows. If it comes ortho to the chlorine group, then we will be getting the product where it will become para to the methyl group. So that's not problem. So I mean, it's okay. if we place the coming chlorine group or ortho to the chlorine group, then at the same time it will also be para to the methyl group. That's okay, perfectly okay, all right. But on the other side, if we place it ortho to the methyl group, then it will become, if we place it ortho to the methyl group, right, then it will be para to the chlorine group. That's also okay, right? But it can't come in between the in between the methyl and the chlorine group. So you will see a mixture of these products, right? But what about the if we have the methyl group and the nitro group, they are in the consecutive positions. I mean, they are at 1-2 positions. So you can see under that conditions, if we subject this compound to the nitration. So what are the available positions for the nitro group? If we place the coming nitro group ortho to the methyl group, that's okay, because under that condition this coming nitro group will be meta to the existing nitro group as well as ortho to the methyl group. But if we place it meta to the nitro group, then what? It will also become, it will be para to the methyl group. That's also okay. So that's why both of the product will result. A little bit homework for you. You can try on it and you have to tell me the product in these 2 slides, that what will be the possible product if we subject these two to any kind of the electrophilic substitution reaction, whether that is nitration or chlorination. In either case, what will be the product? You have to tell me about this. You can make a practice over it and then tell me that which way it has to go. Checked the assignment that I have given to you. In fact, the small homework that I given for the practice, I can see that most of you have did a good attempt in placing the coming electrophile on the benzene ring, which already has 1 or 2 different substituent, especially the ortho and para directing groups, if they are already there on the benzene ring. Now I can see some problems. Whenever you are placing the coming electrophile on the benzene ring, which already has certain substituents, then you have to be very careful looking at the positions where you should be very careful in placing the group. It should be if you have 2 substituent, one is ortho directing and the other is para directing, you have to keep in mind that the group should be obeying the requirement of both the meta directing and the ortho para directing. So you have to choose a positions that is suitable for both the meta and ortho para directing. If that is not the feasible site for both, it means that that reaction will not undergo under that conditions. So the question is that which sometime you are left with only one option, that you have to place, you have only one available positions. Under that conditions, you have to look at the directive influence, that which of the group will precede, which of the group will be predominant, and that I already told you that you have to look at the For instance, if you are comparing, sometimes if you are comparing even the both the ortho-para-directing substituents, then the priority will be given to the one which has a clear electron pairs for the donations. For instance, if you are comparing the OH group with the methyl group, then OH and methyl, OH will be our priority, because OH contains apparent electron pairs. So that's the way that how you will be moving up with the in placing the group. Similarly, if you have the deactivating group like the meta-directing group, the influence will be the priority will be given to the one if that group is highly deactivating. So this is how you will be practicing in placing the certain groups on the benzene ring. Most of you understand this fact, but still you need a little bit improvement in that. It's all about practice. If you are doing a good practice, you will be smart enough to place the group.